Okay, we're going to just sidetrack just a little bit and then talk about magnetos, and then we'll come back to what we're doing. And this is going to be a review for next week. So a magneto is something that is a self-contained unit that creates the spark for the engine. Engines have two magnetos, and the reason why is because you want redundancy. If one magneto fails, you still have another one driving another set of spark plugs. So it's unlike a car where if you lose the battery and then you lose the alternator, the car is going to die because it's a battery ignition system. And we'll go over battery ignition next week. But in a magneto, the first thing you have is you have a rotating magnet. And in that magnet, you have poles. You have a north pole and a south pole because it's a magnet. And within a magnet, as we've talked about before, I believe, that you have lines of flux that find their way from the north to the south. So if this magnet is just sitting here in the air, it's going to look, these lines of flux are actually going to be going through the air. And if you put a piece of paper over it and put some iron filings, you would actually see that. But our magneto rotor is not actually in the air. It is actually contained within a housing. And in the housing, there is a pole shoe. And a pole shoe extension. So pole shoe and pole shoe extension. So this is the extension, this is the pole shoe. And they've got to be very, very close to the magnet. And the reason why they're very close to the magnet is you want the lines of flux to make a path through. Now at the end of the pole shoe extension sits a coil core. So there's the core of the coil, and it's laminated, and these are all laminated here. Why are they laminated? Prevent eddy currents. All right, so right now, this is in what is called full register. And full register means that all the lines of flux, the north is right here and the south is here, so it's in the strongest position. These lines of flux are coming around and going down like this. All right, so they're all traveling through here. Now, even though they're traveling through here like that, you have leakage out of here, we could say. And so a magnetic field is built up around here. And a circular, it expands out, so you have this magnetic field. Well, this rotor is going to turn around and round and round. And right now it's in full register, which would be the strongest point. But in a little bit, it's going to change, so where the north is here and the south is here. And when it's that way, it's called the neutral position. And the neutral position, let this be 0, is on the 0 line. So neutral is here. And full register, I'll just abbreviate, is up here. And so, and it's at neutral, it's here. And it builds up and goes to full register. And then as the magneto starts to rotate more, it's going to leave that full register position and go back to neutral. And then it's going to swing the other way and come back up. And it's going to keep doing this. And so that's what the lines of flux look like if you look just at what's happening with this magnetic circuit. Well, in addition to the magnetic circuit, we have wires that are actually wound around this coil core. I'm not real good at drawing the around the coil core bit there, so I'm just going to represent them next to it. And so I will say that right along here, I have a coil of wire, rather heavy wire. And I'm going to take that and run it over this way, and I'm going to put that on a switch. And so what happens now is I've built a transformer. And if you remember the transformer we built before, where it looked like this, I had a primary, I had a secondary, I had a coil core in the middle. Can you see the similarities? Where did I get my power for this primary coil before? From a what? Okay, from an AC generator. It's plugged into the wall. Something else made electricity and brought it to us. Well, I'm looking down here at the magneto. What's making the electricity in this? Magnetic. Okay, so it's got to make its own electricity. So just like a generator, it's got magnets that are rotating around in there. And so these magnets are going around. Now, yes, I could put everything right next to the magnet, but it doesn't work out well. I got to move this magnetic lines of flux and bring it up here. That's what all of this pole shoe business is about. You got to get it up here, concentrate it up here. And so as this is rotating, so over here with this one, we have something that made the electricity. And when it made the electricity, it made this into an electromagnet, so to speak. Well, okay, we don't have an electromagnet over here. We have a magnet. Follow? So this magnet, it's not what it's called, when it's up here in full register, my lines of flux as they're coming around, my lines of flux are blue, lines of flux are coming out, and what are they doing to that coil? Okay, I got cutting across the conductor. Would anybody else want to throw something out? Expanding across it. Okay, moving across it. These are all wonderful things. The lines of flux from the magnetic circuit are cutting across the windings. Is the magnetic flux flowing through them? No. Absolutely not. There is no flow of them. It's cutting across it. So now we go back to what we talked about before. I have lines of flux, a magnetic field, same word, cutting across wire, which creates a current. All right. Now, if I just take a magnet and put it next to a piece of wire, do I get? No. Have relative motion. Got to have relative motion. What is my relative motion? Is it the spinning rotor? No. It is not the spinning rotor. The spinning rotor does not itself, the movement, it is the way that, over here on the green, it is the way that it builds up flux and collapses flux, and builds it up and collapses it, and builds it up and collapses it. Has nothing to do with the fact that it's rotating in circles. Rotating in circles is how we get it to build up and fall and build up and fall and reverse directions. That just happens to be what it is. But that's down here, this circular bit. So it's, I don't know, it's kind of confusing, but I'm hearing that, well, because it's turning in circles. Not really. If I could leave it there and not move it, but somehow build and contract and build and contract, which is exactly what's happening up here with the transistor, keep saying that. The transformer, it's building and contracting, building and contracting. Is there anything moving up here? Are there any moving parts? No. Okay. So yes, I have a moving part down here. That's not really the point. The point is, again, it's the fact that it is allowing lines of flux to build up to a maximum, cutting across a wire, and then it goes the other way and collapses.
And it also cuts across the coil that way too. When it's collapsing?
Yeah, it's cutting across the coil, that's what I said.
Both ways.
Both ways. It builds up, that's a good thing. It's movement. And then it collapses. That is movement. So as far as this coil of wire goes in the primary, it doesn't care if it was a buildup or a collapse. Build up or collapse. It's happy either way. It's the same to it. Builds up at the same speed, collapses at the same speed. So as far as that one goes, primary, that's fine. Okay, so right now we build up across here. So what does that do in the primary? Right now it doesn't do anything. Okay, so creates a current in the primary. Now, get rid of some of this. So we built a current in the primary. So okay, hopefully everybody could see that. How did I get current in the primary? Relative motion between the magnetic field, the magnetic flux that was generated by the rotor, and the stationary primary wire. I've induced a voltage. I now have voltage in my primary. End of story?
No.
Well, that's the primary. Okay. We'll get into more depth next week. But over here, I have a cam. Right now it's closed. I have a cam. So I get some current flowing through this right here. Well, if I've got current flowing through a wire, what do I create? A magnetic field. So a magnetic field, a true magnetic field, off of a magnet, induced a voltage into and current flow into the primary. Because it induced voltage and current in the primary also builds up its own magnetic field. So now I got this made a magnetic field. Right? Okay, and guess what's next to it? Secondary, with lots and lots and lots of windings. All right, and so the primary builds up and it expands across the secondary. Now, this time it's a little bit different. It builds up, and really it builds up rather slow for our purposes. So in this case, we're not going to use the build up and collapse. It's just going to build up across it, and the secondaries are going, yeah, good for you. You built up across. I really don't care. And we'll get into this next week because it gets more complicated. Once it's built up, this is going to open up. And because of the way I'm going to show you next week, it interacts with this right here. It is going to build up and cause a rapid and sudden, shockingly fast collapse. And because of the relative speed makes a difference. So because of the super rapid collapse of the field of the primary, when I open this switch and kill it, it is going to induce a massive amount of voltage, somewhere in the neighborhood of 20,000 volts. And then from there, it's going to go out to the spark plugs, and I'm going to explain why it does that next week. I'm asking you to explain this during the oral, that the magnet has flux and a field that cuts across the primary. That induces a voltage in the primary. The primary has a voltage which builds up. That cuts across the secondary. When the points open, there is a rapid and sudden collapse of the primary, causing an induced voltage in the secondary, which is a step-up transformer here. You did? Tom, do your oral?
We don't know either.
Questions on this? Yes?
Were you recording?
Yeah.
You're probably not explaining next week anyway, but just want to know the difference between the static flux and EO flux.
Oh, yeah, we are definitely going to get into that. And that's where this curve starts extended out in Lenz's law and everything else. So, but since you guys are really on the struggle bus with this.
I made the short bus for sure.
I said struggle bus.
Oh.
I said you're on the struggle bus. Part of the reason why you're on the struggle bus is because your textbook says something to the... Do you want to say it? You say it very well. No, she'll want to say it.
Go positive.
No. Sophia can dang near quote the book, which is something to the effect of the magnet goes around, there's lines of flux that travel, and because of that, there is an induced voltage. Or something. I think that's even more information the book has. Induces current.
Well, that's what I wanted to add, because then after that it says once the polarities switch and you get to the E gap past neutral, and then the switch opens, it's like it induces more flux, and then that's what causes the jump from the primary to the secondary.
Yeah, that's like basically what it says.
Yeah.
So we'll cover that. It gets into a lot more depth where this I don't. We'll take up the rest of the day with that when we used up too much time. But this is what you need to know, really. I mean, right now. I mean, the E gap stuff is going to be very important, but this will get you through it. E gap. What is E gap? This is what I'm not going to write it. This is what you should write down. I say, what is E gap? You should say it is the number of degrees past neutral at which the points open. That's all I care about. The number of degrees past neutral at which the points open. And why neutral? Because neutral is right here. Why not here? Because this is the most change. And 10 degrees past is right here. And it looks Christmassy. And so what happens is because of Lenz's law, as this starts to fall out, the current in the primary does not want to follow it. It hangs on because of, remember, Lenz's law as one thing. So it's out here. And so there's all this stress on the, they call it in your book says there's stress on the magneto because the magnetic flux, the true magnetic flux off the rotor is all the way down here, and this is still open. In a minute, it's going to start following it like that. But hey, why not just open the points right here? And so instead of it starting to fall off, it's got nowhere to go. And so it's going to come all the way down here. That's a massive amount of change. We're looking for that change, sudden and rapid change, and that's how you're going to get it. So, all right. Back to our regularly scheduled program. That was not good to say.
I can't. I don't remember how to do it on this thing. Oh, you just drop off. There we go. Look at that. I don't remember how you got it. It was something like they put a box around it.
Let's. Oh, we can get back to that later. Okay, everybody's pencils are sharp? Yeah.
Is there any questions on your test about logic gates?
Yes.
Yeah.
This week there was.
Absolutely.
Okay.
So guess what I'm going to talk about right now? Logic gates. Now here's the wonderful thing about the FAA, and they make them very simplistic for us. And it doesn't appear that there's any sort of electrical input. They just work. It's like, well, how can two opens produce an on when there's nothing going through? But that's okay. Huh? That's like the Q&A ones? Yeah. All right, so logic gates. Logic gates. Make sure I'm at the right spot here. Yep, logic gates. All right. They are functions performed by, for some reason I wrote computers or circuit boards, and then I crossed out computers. Somebody probably argued with me about that.
Probably
But
not.
I'm going to write anyway, computers or circuit boards.
Watch him complain tomorrow when we watch the video.
Doesn't. All right, it is based on Boolean logic. You ever heard of that one?
Nope. Just did.
Boolean logic. If you haven't, I bet Prince has Boolean logic, right? Huh? Have you?
Yes.
Okay then. and where is Boolean logic actually used most? Huh? Computers. Believe it or not, Google actually allows you to use Boolean logic in your search engines.
You put it in soup.
Huh?
You put it in soup.
Soup, yes. Trying to think of a good joke on that. Boolean logic of and or not. So when you're, I don't know if anybody does this, when you're searching something on Google, like, it's something crazy that always comes up. Well, tell you a fun story. When I started doing this was before computers, and then, as I was, computers came along as I was in the industry, and there's this thing called Roseanne studs that are used on engines, and they're horrible, and I hate dealing with them, and I'll explain it in some other time. But more or less, it's a stud that goes into something that's got a locking ring that it pounds into the base metal, into recess. What? That's a Roseanne stud. I don't know. Anyway, you have to have a cutter, and it goes over the stud with these teeth. It goes down and it cuts out the lock ring. You got to pull it out without ruining the base metal. And anyway, I was in need of a new Roseanne cut stutter. And so, as anybody would do with computers that are new, you go to the computer and you type in the word stud.
Okay.
Did not go well for me there. So I could have used Boolean logic and put stud and then capital words not, and then something like Magic Mike, So you can actually use Boolean logic words in Google. Probably not the best example, but it's one came to mind. Sorry about that. There are 7 commonly used ones. And the bad news is, outside of just memorizing them, I don't really know what to tell you on that one.
Remember what the base was? You can kind of guess the other one.
Yeah, you can if you memorize some of the simple ones, you can. So logic gates. Well, we'll do the 7 of them. 1. So we'll start with the and. And with each one, there's a truth table. And so if you understand the truth table, it kind of makes sense to it. So an and is where all inputs must be 1. Must be 1. And 1 is on, basically, to produce a 1 out. All right, and so that looks, I should probably just get some pictures of them. Like that. So these are the inputs over here. So this is input, this is the out. And so if I look at a truth table, inputs, outputs, we have pin A, pin B, so pin A, pin B. So if A is a 0 and B is a 0, the output will also be 0. If I have a 1 and a 0, meaning this is on, this is off, then the output is also going to be 0. That's a 1 and that's a 0, that's a 0, and a 1 and a 1 equals 1. And if I were going to draw this in a analog type way, it would actually look like 2 switches. I could say the light be on. So if So if switch A is closed and switch B is closed, then I get an output. If B is closed and 1 is open, B is closed, 1, and A is open, the light's going to be off. All right, so it's just an analog way of looking at it. So that's your and. Have an or. So number 2 would be or any input, input of 1 will produce 1. Will produce 1. So that one looks a little more like that, not quite. So truth table, so input, output. Last year I did this on the board, so I could just keep erasing this right here. Let's see, truth table. So A, B. So 0 and a 0 would be 0. Okay, so that's A, B. Any input of 1 will produce 1. So 0 and 1, I get a 1. All right, you got it. 1 and 0 is 1, and 1 and 1 is 2. 1.
2.
Let's see. I can do analogs for some of these. Then they start to get complicated. So that's kind of like this. So either one of those closed, we're going to get. If they're both open, the light is off. If A closes, the light's on. If B closes, the light's on. If A and B are closed, the light is on. So 3. 3, 3, 3. All right, an invert or not. Invert or a not. Reverses the condition. Oops, reverses the condition. And basically what that is, anytime you put a little circle, a little dot on something, so like this one is a triangle, that little dot means change everything around. Yeah, the analog for this one's very difficult, but I made one up. Input, input, output. Oops, I'm sorry, I think this one only has 1. There we go. Make it correct. There we go. So input, an input of 0, and you're going to get a 1. An input of 1, you're going to get a 0. Okay. You want to see my analog for this one? All right, give it a shot. All right, so there we go. So this is the input right here. So with a normally closed switch here, this is the input. So whenever the input is open, the light will be on, right? And then if I close the switch, since this is normally closed, this will energize this, opening the switch, and that will be off. So when this is like that, that probably takes more explaining to do than just the... Yeah. All right, I got 4. The NOR, which is also called an inverted OR. Inverted OR. So, all right, input, output. This time it's got A and B, and C is out. So A, B, C. All right, so now we're just going to invert it. So if inputs are 0 and 0, output's going to be?
1.
Oops, I forgot to put this. There's the invert. 1. 0, 1, 0, 1, 0, 0, and 1, 1, 0. All right, you guys are doing great. So 5 is the NAND, N-A-N-D, which is inverted, and. So we just take the and invert it. Circle. So a 0 and a 0 is going to equal a 1. 1 and a 0 would equal a 1. Because in an and, you should have 1 and 1 should be a 0. So just remember to invert it. So 0 and 1 is going to be 1, and then a 1 and 1 is going to be 0. So 5. 2 more to go. 6. Exclusive. Exclusive OR. Design to produce a 1 output whenever input is dissimilar. So this one's a little different looking. So let's go with this. There we go. A, B, C. So input, output, pins A, B, C. So input, 0 and 0 is going to be a 0. Produce a 1 when output is dissimilar. 0, 1, 1, 1, 0, 1, 1, 0. Last but not least, of these 7 common ones, the exclusive NOR, which produces a pattern. I should say an output pattern. Output pattern exactly opposite that of an exclusive OR gate. And that would look just like the one I just drew. With the circle meaning invert. So input, output, pins A, B, and C. Input, so if I have a 0 and a 0, I'm going to get a 1. And a 0 and a 1. 0, 1, 0, 0, 1, 1, 1. All right. Like I said, other than just trying to memorize them, which you know I'm not a big proponent of memorizing stuff like that, I have Electrodroid, and it has all of them.
Is that a map?
Yep. Let me see.
Can we use that on the test?
I'm not going to let you use my phone on the test. At least I thought it did somewhere.
We bring our own.
Your own phone? No. Maybe it doesn't have it. I thought it did somewhere.
What's it called?
Electro Droid. Oh, Boolean logic gates. There we go. And, or, not, NAND, nor, XOR, and XNOR. Yeah, I got all the 7 up there.
You know what confuses me is the
Wait.
try gate.
Don't even have to worry about them.
It's on the program.
Huh?
It's on the program.
What program?
Logically.
Oh, it's not an FA thing. All right, I believe.
XNOR is the exclusive NOR, right?
Yes. Is it? Wait, I said yes.
Yeah, it's
exclusive
XNOR is
NOR.
exclusive.
XNOR is, yes, this one right here. XNOR. That's EX or XNOR. So it's just take the X. So it's XNOR right there. XNOR.